Okay, I hope my voice is clear and my screen is visible to you. So, so let's start our eighth tutorial. So it is clear, voice is clear, right? And voice audible, right, Sandeep?
Yes, sir.
Yeah, thank you. And today is 15th March. Okay, so today we'll start before doing usual assignments problem. I'll start some problem from normal problem. I will start to do the some normal problem theorems and some normal problems. So I'll discuss something regarding the primary decomposition theorem, and I will discuss some problems on basis of those. And after that, I will go to some other problems as well. Okay. So what primary decomposition theorem says. Primary decomposition theorem. What it says, let T be a linear operator on a finite dimensional vector space. Let T be a linear operator on a finite dimensional vector space V over a field F, and let P be the minimal polynomial, minimal polynomial for T, and Px is equals to P1 R1 all the way Pk Rk, where P1 Pk all are irreducible monic polynomial, all are irreducible monic polynomial, over a field F. Okay, and the Ri are positive integer. Let Wi be the null space of this operator pi t whole to the power ri. So pi is polynomial, so one can easily make sense pi t and pi to the power ri as well for all I equals to 1 to k. Then first one v is actually direct sum of w1 all the way direct sum of wk, and second is that each wi is invariant under T. Okay, and third is that if Pi is the operator induced by restricting induced on Wi by T, then the minimal polynomial of Ti is Pi to the power Ri. Minimal polynomial of Ti is pi to the power ri. Okay, so if you want to do some problems, first you have to maybe obviously you may not able to remember full proof of this theorem for all the time. But if you want to do solve some problems, so here you have to understand what wi is and from where this w are coming, and all these details I just want to say. So before going to any problem, I just want to discuss what are the materials here using. Okay, T be a linear operator on a finite dimensional vector space, and let's dimension is fixed and it is n over a field F, and Pi be the minimal polynomial for T, and Px is equals to P1 x and Pk all x, P1 to the power R1, Pk to the power all the way up to Pk to the power Rk, where P1 to Pk are irreducible monic polynomial over F. So here irreducible over F means that P1 can be like P1x can be like x plus 1, x square plus 1 if the field F is equals to R. So in that case, P1 can be x square plus 1, because x square plus 1, this is a polynomial which is irreducible over R, but this is reducible over complex field C. In fact, any polynomial is reducible over complex field C, because C is algebraically closed. So it is irreducible over R, but in complex plane it can be written as x plus I x minus I, where I is the square root of minus 1. Okay, so whenever field is complex number, so depends on what field we are considering. So on the basis of this, irreducibility will be there, but monic means the coefficient of the highest degree term will be 1. That is what means the monic polynomial. Okay, now the fact what I just want to share here is that from where this wi and wk are coming. Okay, wi is clearly saying that wi is actually the null space of pi to the power I. So this is basically, I think it is written here. So this is the null space of the operator pi to the power ri. Okay, that is okay. And why this each wi is invariant? Why this each wi is invariant? If you remember, if I
Null
consider,
space is
yes,
always
null
null
space,
space is always invariant subspace.
yes, null space of this operator. And why this null space? I mean, for example, if you remember, I think I have discussed this thing also. If T and U are two linear operator on a vector space V, and ut equals to tu,
When
that
they
means T commutes,
commute,
then the
yes,
range space and null space all will be, I mean, range space of T will be invariant under U, null space of T will be invariant under U. Similarly, range space of T will be invariant under U, and null space of T will be invariant under U. So the same fact is happening here, because Pt, this polynomial Pi to the power Ri, this is invariant. This is commutes with the operator Ti. That's clear, because you can just I mean do the usual computation, you will get that this is what happening. Okay, so yeah, recording is okay. So that's why the null space is this wi is invariant. Okay, but but what I want to say here is that there this wi is is considering as a null space. This wi also can be given as the range of some operator ei on the vector space V. And what that operator, that is ei, I am just saying, say what this operator ei is, what this operator ei is. Ei is something like, for this I just want to write, because why I just want to discuss this ei, because whenever you will be facing some competitive exam, so there you need complete full details of each proof. Okay, where each term is using, so that thing is needed for nowadays competitive exams. So now, for example, here considering p1x, and all the way we have p is equals to px is equals to, we have p1x whole to the power r1 all the way pkx whole to the power rk. Now if I consider fix, then this is equals to just write it as px by pix whole to the power ri. So that means I am taking all the element from here except the ith position one. Okay, so so if we consider this way, this is again a polynomial, because p1 ax whole to the power r1 all the way pi minus 1 ax whole to the power ri minus 1 pi plus 1 ax whole to the power ri plus 1 all the way pkx whole to the power rk. So this is again a polynomial, but note that this fi f1 all the way fk are they are what is that is called, they are prime to each other. I think the term is that GCD is one basically. They are distinct prime polynomials. I think relatively prime. Yeah, that's they are relatively prime. Relatively prime. This is the term using relatively prime. So that means we know that if two terms or more terms are relatively prime, so there exists some polynomial g1 all the way gk such that summation of gi fi is equals to identity. This is what happens for a principal ideal domain, and here the space of all polynomials over a field real number or complex number or even rational number, those are principal ideal domain. Okay, they are principal ideal domain. So G1, G2, Gk such that Gi Fi equals to T1. Okay, so in particular, if I take Hi equals to Gi Fi, then Hit, that is also can be making sense. This is equals to taking as Ei, and range of this Ei is equals to Wi. Okay. And why the third one will satisfy that Ti is the operator induced on Wi by T and the minimal polynomial of Pi to the power Pit to the power Ri. That I will not say here. When I will going to the Jordan canonical form, there I will say. But on the basis of this, I will just discuss one problem. Maybe not in the standard way that having some four options, but I will try to. I'm just taking in standard. Okay. Taking some problems and try to solve that problem. Okay, just 1 minute. Okay, now we have all these things. Now I'll just go some little more in the theorems. If in addition each pi are linear polynomial, or the field f is algebraically closed, then automatically all other element will be linear polynomial. I mean, irreducible polynomial will be the only linear polynomial. Algebraically closed. In that situation, if in addition each pi are linear polynomial or f is algebraically closed, then then polynomial px will be something like x minus c1 whole to the power r1 all the way x minus ck whole to the power rk, and c1 or ck are distinct eigenvalues of the operator t. Then if we consider that the operator ei, that is equals to t minus lambda ci identity, that is these factors only. I'm not going to powers. This ei now range of ei is the null space of wi of, okay, just okay, yeah. If ei is equals to, okay, in that situation ei will be that way, not sorry, so not this way. Ei, we have seen what ei here it is, that ei is equals to this gi fi and taking it is as ei. So okay, yeah. So then if we consider D is an operator, that is C1 E1 plus all the way CK EK. EI, what we know, what EI is from here, that EI is something whose range is WI, which is the null space of TI minus T minus CI whole to the power RI. Okay. So then this is then clearly then D is a diagonal operator. This is directly diagonal operator, I think. So one can more generally write D is a diagonalizable operator. Now note that these EI are projections here, as we have summation of GI Fi is equals to 1 and Hi equals to GI Fi and Ei equals to Hit. So what will get I equals to 1 to k, that will be identity. Okay, So therefore, using this fact, one can write T is equals to T of summation of I equals to 1 to K. That can be written as summation of T I equals to 1 to K. Okay. Then note that consider n is the operator, that is T minus D, that is summation of I equals to 1 to K T minus Ci identity whole into Ei. Okay. Now this is something diagonal operator, but if I consider some power k, that will be summation of I equals to 1 to k t minus ci identity whole into k. Okay, this is same k, so let's change it to r. So change it to r uh, into ei. Why it is happening? Because here only, not only we have this fact, the second fact is that ej is equals to 0 if I not equals to j. Okay, this is also there, so that will used, and ei square is equals to ei. Okay, so that fact will used and we'll get this one. Okay, now we know, I mean, if we take r is equals to LCM of this r1 all the way rk, where r1, r2, rk is the power of this p1, p2, pk. So then what will happen? Because in that situation, this n to the power r will be 0. And that implies n is a nilpotent operator. N is a nilpotent operator. So main fact is that here, what main fact is that, so what we are getting here is that n is the equals to t minus d. D is the diagonal operator and n is the nilpotent operator, and t is such an operator for which the characteristics minimal polynomial is completely factorized. Okay, and we know that if the minimal polynomial of an operator is completely factorized, that operator is triangulable. Okay, that means there exists an orthonormal basis with respect to which the matrix representation of T will be triangulable. And basically saying the fact is that if we are on algebraically closed field, where algebraically closed field is something where any polynomial is completely factorized in linear factors. So that's why there it is automatically minimal polynomial is completely factorized in linear factors. So there automatically will have this one. So we have n equals to t minus d. That implies t equals to d plus n. Moreover, which I am not writing here, moreover, dn equals to nd, that is commuting. Okay, so that means every linear operator t for which the characteristics polynomial, sorry, or minimal polynomial, characteristic is also same, characteristics polynomial or minimal polynomial is completely factorized, that can be written as a sum of diagonal operator and a nilpotent operator. Okay, and such that this diagonal and nilpotent are commutes with each other. Moreover, they are unique up to unitary equivalent, I think. Okay, but those things I will not prove here, but from here I will just prove one problem. I will try to solve one problem. Let's take a is equals to 3, 1, minus 1, 2, 2, minus 1, 2, 2, 0. This is an operator, a linear operator. So this is a linear operator on R3 whose matrix represent is whose matrix representation is this matrix A with respect to standard order basis. Respect to standard ordered basis. Okay, so that means Tx is equals to T is an operator from R3 to R3, and Tx is equals to Ax. This is what it is means. So now what are the questions here it is given? So that the diagonalizable operator D on R3 and nilpotent operator N on R3 such that, so what you have to find, so that there exists a diagonalizable operator D and on R3 and a nilpotent operator in on R3 such that t equals to d plus n, dn equals to nd, that is commuting. We know what is the guaranteeing this all these things, that is the minimal polynomial is completely factorized. Now the main problem is that find the matrix D and N. This is the interesting part. Okay, so find the matrix D and N. This is what we need to do. Okay, so find the matrix D and N. So suppose, for example, if you want to think this is as a problem which has options, so assume D and N any random matrix, whatever will be the correct option with that. Okay, so matrix A here is the 3 1 minus 1 2 2 minus 1 2 2 0. So first work is, as usual, we have to find the characteristics polynomial. Okay, so a minus 1 is determinant of a minus 1 is 3 minus lambda 1 minus 1 2 2 minus lambda minus 1 2 2 minus lambda. So this is will be little tricky, I think. This is equals to 3 minus lambda first one, this is minus lambda 2 minus lambda minus plus 3 minus minus 2 lambda plus 2 plus minus, this is minus 1, this is plus 1 means minus, this is 4 minus 4 plus 2 lambda. I think I'm correct. 3 minus lambda minus 2 lambda plus lambda square plus 3 minus 2 minus 2 lambda, that is minus 2 plus 2 lambda minus 2 lambda. Okay, so plus 2 lambda minus 2 lambda will be cancel out. I hope I'm correct. So this is 3 minus lambda square minus 2 lambda plus 3 minus 2. Okay, so 4 is a clearly 4 is a eigenvalue because every row sum is 4, so therefore 4 is an eigenvalue. So let's see whether we are in correct direction or not. Lambda 3 lambda square minus 6 lambda plus 3 lambda square minus 6 lambda plus 9 minus lambda cube plus 2 lambda square minus 3 lambda minus 2. Okay, so this is equals to 5 lambda square 6 lambda minus 9 lambda minus lambda cube plus 7. So 4 is satisfying or not? 5 into 20 minus 9 into 4 minus 64 plus 7 36. This is 100. I think I made a mistake then. Okay, just 1 minute. 3, sorry, not 4. 3 is the not 3 as well. Sorry, this is not correct. Okay, so this is the option. So if I write 1 here, 5 plus 6.
Sir,
Yes.
I think 8 lambda is there, sir.
Huh?
8 lambda.
This is 8 lambda, right? No, 6 lambda, 3 lambda, no? Okay, just let's check the correct. If it is correct, then no problem. Just I have not checked on this. 3 minus lambda, 2 minus lambda, 2 and 1. Oh, I got it. Here I have made the mistake. So this will be then. Okay, I think here I have made mistake. Minus lambda, 2 minus lambda, that is minus 2 lambda plus lambda square, 2 and 1 minus 2 and plus 2. This is correct. So plus 2 this is, and lambda square, and here it will be minus 1, 2 minus 2 and minus lambda, minus 2 lambda, minus 2 plus 2, that's correct. And next one is the minus 1 is here, and 2 to 4 minus 4 plus 2 lambda, yeah. So this will be 2, yeah, you are correct. 2 lambda, this full thing will be then incorrect. You're correct, thanks. This is 3 lambda square minus 6 lambda plus 4 minus lambda cube plus 2 lambda square minus 2 lambda minus 2. So this is equals to 3 lambda square minus 8 lambda, sorry, 5 lambda square, 5 lambda square minus 8 lambda minus lambda cube plus 2. So I think if we replace lambda equals to minus 1, then what it will happen, 5 minus 5 plus 8 plus 1. Okay, so replace plus 1. So what will happen, 5 equals to 5 minus 8 minus 1 plus 2. Still it is not. I think there is a problem. Next a minute.
So there should be minus 4, sir.
Where? Here? Here?
No, sir. Last one, sir.
Here?
You can take a plus 4, sir. Plus 4.
No, no, there is minus 2, no? This minus 2 is carrying.
Sir, sir. So
Yes.
characteristic polynomial of a 3 cross 3 matrix is given by x cube minus trace a x square plus trace of adjoint
Plus 2.
a
Trace
x
is
determinant.
3 to 5. Yeah, so that is here. Okay, so
Yes, sir.
determinant.
This is
What is the determinant here?
you just check it, sir. The
Okay.
determinant I am getting 4.
Determinant is 4, right?
Yes, sir.
So if determinant is 4, then I am making mistake. That's true. So let's check determinant. 3 into 0 minus plus 2 minus 1 into 0 plus 2 minus 1 into 4 minus 4, that is 0. That doesn't make affecting anything. So this is equals to 3 to 6 minus 2. Yeah, you are correct. This is 4. Determinant is 4. So therefore I am making very big mistake then. 3 to 6 here. Okay, that I am making mistake. 6, and so this will be 4. Correct. Yeah, 3 lambda square minus 6 lambda plus 6. That's 3 lambda square plus minus 6 lambda plus 6 minus lambda cube plus 2 lambda square minus 2 lambda minus 2. This is the correct. So lambda equals to, if I replace 1, then yeah, then that's correct. Lambda, if I replace 1, then 5 minus 8 minus 1 plus 4 equals to, yeah, lambda equals to 1 will be a factor. So let's factorize it. Lambda minus 1.
4 is not an eigenvalue, sir.
Yes.
4 is not an eigenvalue of the
No,
matrix, sir.
1 is an eigenvalue. I'm just talking about 1 because it is satisfying by 1. So one can write lambda cube minus 5 lambda square plus 8 lambda minus 4. So this is the thing, okay. So lambda equals to 1 is an eigenvalue. So one can write lambda cube, sorry, lambda square. So this will be lambda cube minus lambda square minus 4 lambda into lambda minus 1 minus 4 lambda square plus 4 lambda plus 4 into lambda minus 1 plus 4 lambda minus 4. Yeah, this is. So this will be minus lambda minus 1 lambda square minus 4 lambda plus 4. So this will be minus lambda minus 1 lambda minus 2 square. So this is the characteristics polynomial. Okay. So this is the characteristics polynomial. So characteristics polynomial is lambda minus 1 into lambda minus 2, or it is written in general in terms of x minus 2 square x minus 1. So clearly the characteristics polynomial there is completely factorized in completely factorized in linear factors, completely factorized in linear factors. Therefore, and in particular, as characteristics polynomial is completely factorized in linear factor, so minimal polynomial will also be completely factorized as linear factor, because minimal polynomial is something coming from the characteristics polynomial. In particular, minimal polynomial is completely factorized in the linear factors. then there exists a diagonalizable matrix D and nilpotent matrix. Recall again, nilpotent matrix means the matrix for which the some power will be 0. Okay, that means for that matrix the minimal polynomial will be x to the power k equals to 0, and characteristic polynomial will be again x to the power k equals to 0, something like that. So nilpotent matrix n such that t equals to d plus n, and these d and n will commute with each other. So now question is how to find d and n. So this is
But this
this
is
answer.
coming from this primary decomposition theorem,
Right,
right?
primary decomposition. I mean, whatever discussion we have done here, that one can take D operator is something like this, summation of Ci Ek, okay, Ci Ei, and take
Yes.
N is something T minus D. So this is something a theorem I'm proving, but not writing it in form. If we have primary decomposition theorem, after that assume that the minimal that factors are all linear factors, okay, and that is possible obviously when we have what is called algebraically closed field, but even without algebraically closed field this is possible. Okay, so if we have algebraically closed field, then in that situation it is obviously happen. Okay, so from there one can say this way. Okay, yeah, I mean this is possible from primary decomposition theorem. Only one fact is needed, those pi is linear factors. That is what we can say. So now I have to find d. So recall that d is equals to, if we find d, then we can find uh, n by just
Right.
taking t minus
T
d.
minus.
Yeah, that's it.
Yes.
So d equals to summation of ci ei. Okay, but what is ei? Ci is known. What is ci? C1 is 1 and C2 is
P
2. Yes, but
I
before,
K. Yes, sir.
yes, so before that I need to find
Minimal
what,
polynomial.
yeah, minimal polynomial. But minimal polynomial, we have to find what is minimal polynomial. We can do two things to find minimal polynomial. One is that okay, one is that to find minimal polynomial, as we
Sir,
have a,
there are only two possibilities for minimal polynomial, sir.
yeah,
One
that's
is where
true, x
x minus.
minus 1, x minus 2 square, and another is x minus 1, x minus 2. Okay,
Yes,
this is,
but
and
only
if
we
we,
need annihilating thing, sir.
yeah, if we know this is the minimal polynomial, then we can say that t is diagonalizable. Then obviously this n will be 0. There is no role of n, because t itself is diagonalizable, and t can be written as summation of ci ei, where this ei is coming from this what is called our Lagrange's polynomial. Okay, but okay, forget about those. Let's check what is the thing. So but even to find minimal, which one is the minimal polynomial, there is two options. One can check a minus identity, a minus 2 identity is equals to 0. This is one option, and other option is that we have to check the eigenvector of the a minus 2y. If only one eigenvector is there, then obviously minimal polynomial has to be this one. If we have two eigenvector, then minimal polynomial has to be this one. Okay, because if we have, because why I'm saying this, because here we have only two eigenvector, 1 and 2. As one is eigenvalue, there must exist an eigenvector. Okay, let's take it is e1. If 2 is eigenvalue, then it at least will have one eigenvector, that let's take is e2. If it has two eigenvector e3, then obviously the operator t has, I mean v has a basis consisting all eigenvectors, so that will say diagonalizable, and that will say minimal polynomial is this. Okay, so you can go both way. So let's check eigenvector, because eigenvector is shortest, I think. So I believe, let's check whether eigenvector is shortest or not. So a minus 2i whole, write it as x1, x2, x3 is equals to 0. Then a minus 2i is the matrix. This is 1, 1, minus 1, 2, 0, minus 1, 2, 2, minus 2. This is a minus 2y. This one with x1, x2, x3, this is equals to 0. So what we are getting? x1 plus x2 minus x3 is equals to 0, 2x1 minus x3 is equals to 0, 2x2 plus 2x3 minus 2x3 is equals to 0. So these two are actually same thing. So
Yes, sir.
they are actually, we have these two factors, x1 minus x3 is equals to 0, 2x1 minus x3 is equals to 0. So obviously what one can do is that one can replace, let's replace x3 is equals to 2x1 from here, we'll get, and replace this one here. So what will give, x1
There
plus
are two.
2x2 minus, yeah, there
We
are
need
two. So that
to.
means we already done, we don't need to find separately the vector n. Okay, so x1, so x2 is equals to x1, so one can choose 1 1 0 as an eigenvector, and another is, I think, 0. Okay, sorry, there is two eigenvector, x1, no, that's
X3
not
is
true.
2x1, sir. 1, 1, 2.
1 1 2, that's true, but there
Hmm.
is one eigenvector, na? Two eigenvector is not there.
Why?
One eigenvector is there only, because x1 equals to x2 and x3 equals to 2x1. So that means if we fix x1, we are getting all other vectors.
Yes, sir. Yes, sir.
So that means the minimal polynomial. So there is only one
Not
eigenvector.
diagonalizable, sir.
Huh?
Sir,
Not
you might say
diagonalizable.
not
Not
yes, sir.
diagonalizable. It is not diagonalizable. Eigenvector corresponding to lambda equals to 2, because here arithmetic, sorry, algebraic multiplicity is 2, right? X minus 2, x minus 2 square, but the geometric multiplicity is 1. Okay, so that's it is not diagonalizable. So that means we have null operator and d operator. Okay, so that implies the t is not diagonalizable, t is, or a is not diagonalizable, a is diagonalizable, and that implies the minimal polynomial is x minus 1 x minus 2 square is equals to 0. So this is the minimal polynomial. Okay, this is the minimal polynomial. So now,
E1 is t minus I and E2 is t minus 2 whole square.
e1 is equals to, you are saying, t minus I,
Yes,
and
sir.
e2 is equals to t minus, I think this is 2i, this is
2I
I,
square.
this is I, 2i square, this is I. But not only
Yes.
this, I think there must be some other thing as well, and that factor is, I think, 2 minus, here it is 1 minus 2, I think, minus is, no, minus is not possible. There is something such that we need this polynomial is okay, x minus 1 is another, x minus 2 is another polynomial, but we need some polynomial g1 x minus 1 plus g2 x minus 2 square is equals to 1. We need that one, g1 and g2 is needed here, otherwise it is not possible. Okay, so how to find g1 g2, so that one can directly go. Okay, so just 1 minute. Gi will be that is those will be the Lagranges, I think, but let's check once whether this is correct. I'm saying G1 and G2 to Gi.
Sir,
Yes.
can you go to the article where you have shown these things, sir? Sir, I
There.
am not clear about, sir.
Sorry.
Sir, I am not clear about E1, E2, E3.
E1 E2 is there. I'm just going. E1 E2, how E1 E2 is taking? Note that Wi is the null space of Pit to the power Ri. Okay. They are not
Yes, sir.
Ey. Pit to the power Ri is not Ei. Ei should be something for which Wi is actually range space. Okay. Okay, so now
Okay,
just
sir.
so, and from where this ei I will get. Okay, if I consider pi, we have this full pi. Let's take fix is equals to this px by factoring the only removing the ri position, I position, that is where it is I position is here, there that I will remove, then we will have this particular thing, except this ri is missing here. Okay, so now this f1, f2, fk, they are relatively prime to each other. That means this f1, f2, gcd of them is 1. So that's why there must exist g1, g2, gk. We know that this if a, b, c, three terms are relatively prime to each other, then there must exist a1, b1, c1, such that this is equals to 1. And this happens
by
whenever
Euclidean algorithm, sir.
in a principal ideal domain it will happen. I don't know what's algorithm, but it is
By
principal.
Euclidean
I think it.
Euclidean algorithm, na sir. By Euclidean algorithm.
So the same thing happens here for polynomial as well, but this gi needs to be find. So that gi I just want to trying to find. Okay, gi is also there is a formula. That formula I'm trying to find. This gi. Okay. When once this gi is obtained, this summation of gi is 1. That is what I am taking. So if I take hi is summation of this gi fi, then ei will be hit. Then we have this all these things. The summation of ei is identity. Some ei ej equals to 0 whenever I not equals to j, and ei square equals to ei. That means they are all projections and sum of
So
all those things.
EI,
To get ei, we have
so
to find.
EI sir actually HIT sir.
Yes, HIT.
HI.
That's true. That's true. So
GIFI.
Fi is known. Fi is known. Fi is f1.
Okay.
In our case, it is x minus 1, and in the another case x minus 2. So, but the fact is that what is the
Yes.
gi that I have to find? Just 1 minute. We have formula. I think. Okay. So here we have to find g1x and g2x such that these two will be okay. So so g1, I'm just, for example, if I write it is as a single order polynomial, there is a way, that way I just don't want to go. Okay, let's take g1x is equals to, I mean we have to compare coefficient, that is what we have left. Okay, g1, g2. Okay, for example, so what we'll have, g1 into x, this is a polynomial again, minus g1, that is again polynomial, plus g2, x square minus 4x plus 4 is equals to 1. So what will get, g1x minus 4 g2x, this should be 0. So g1 is equals to 4 g2, this is one way. And other this is first fact. Other fact is that g1 as a polynomial, no, not this way, not this way, g1 x minus 1 g2 x minus 1 square is equals to identity. This is Lagrange's polynomial, as I know. Okay. So if I take g1, g2, just g2. G is the polynomial.
Sir,
Yes.
you can write it as, sir, 1 is equal to x minus 2 square minus plus 1 minus x whole square. Sorry, minus x minus 1, 1 minus x.
Yes. G.
I think so. There
No,
is
no,
some.
no. I can write that. I just actually basically I just want to. I don't want to go more than. I mean, go beyond all these things. So, but still I have to go. I think if I write G is this way, so then G1 AX with G1 AX, this with and G2 AX is. I'm writing 2-degree polynomial, for example. Okay. It may be above degree polynomial, but that does not affecting that much. But okay, if I write this way, then it will be very big problem. So that's why I just don't want to write. There must be some easy way which I'm not able to recall right now. X plus a2 x square.
Sir,
Yes.
sir, you can use Euclidean algorithm, sir, to
No.
find this, sir. This thing, sir.
That
Sorry?
division formula, right?
Yes, sir. From we can use GCD of AB is equal to GCD of BR, sir. Where R is a remainder term, sir. So write, sir, x minus 2 whole square in terms of x minus 1, sir.
If I want to write
Ah,
this way, one can write. I have to write that's x minus 1 square plus 2x minus 1 plus 1 in this way.
sir, divide x minus 2 whole square by x minus 1, sir.
X minus 1,
Ah,
but so that situation, how one can divide, there is no factor, no factor is there. X minus 2 whole square does not have any factor x minus 1, so it will not be divisible. X minus 2 square is not divisible by
there is
x1,
some remainder term, na, sir?
so remainder term is
Right?
full term here.
Sir, sorry, sir.
Remainder term is the full term here, x minus 2 square. If we do the, okay, this is the term, x minus 2 square can be written this way. So now divide x minus 1 square by dividing x minus 1. So dividing this one. So what I will get, I think remainder will be 1 here in that way if we just want to say. Yeah, remainder will be 1 in that way. So after that, what we have to do?
Sir, minus 3x plus 4 minus 3x. Sir, what is the quotient, sir?
Quotient will be x minus, I mean, basically if we divide, so basically what I'm saying, x minus 2 square, if we divide x minus 1, so so it will be first x minus 1 plus 1. This is the quotient, I mean x minus 2 whole square is equals to x minus 1 plus 1, that is x, I think, that is x, sorry, that is x plus 1 into x minus 1 plus 1
X minus
minus
3x
x minus
plus
1.
x minus 3, sir.
This is
Minus
the,
3 times.
so
Uh,
this is the this is the dividend, and this is the quotient, and this is the remainder.
no, sir. This will not work here, sir.
This process
We
will not
need,
work.
sir, you are getting only, sir, x square minus 1 minus 2.
Huh?
So x square,
Oh,
this is
oh,
x
oh, right,
minus
right,
2.
right, 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 right. So
So
I have made
first
some mistake.
expand x minus 2 whole square as, sir, x square minus 4x plus
That's
4.
true, that's true, that's true, that's true. I have to write. This is x minus 1 whole square plus 2 into x minus 1 plus
Sir, sir,
1. This is the thing. So now if
sir.
we divide, yes,
X minus 2 whole square can be written as x minus 3 into x minus 1 plus 1.
really,
Yes, sir.
x minus 2 square you are saying.
Yes, sir. Yes, sir.
Ah, that is true.
Yes, sir.
X square minus 4x plus 4. But you are saying that this can be written as x
X minus
minus
3
3,
times x
x
minus
minus
1
1.
plus 1.
Yeah, so in that way, remainder is x minus 3 and
No, no. Remainder
the
is 1.
remainder is 1 and the
Quotient is x minus
quotient
3.
is x minus 3.
Yes, sir.
So now next we have to divide x minus 3 by x minus
No,
1.
no, no. Why you are dividing? Just write 1 is equal to x minus 2 whole square minus x minus 3 times x minus 1. This will work, sir, for our purpose.
That's true. That's true. Exactly.
Yes,
That
sir.
works. That
3
works.
times x minus 1.
Yeah, as we are getting one, so we don't need to do. That's true.
Yes.
That's true. Yeah. Maybe this is the way. That is, maybe this is the way. Exactly, this is the way. Thanks. So we have to x minus 1 square. So 1 is equals to minus x minus 3 into x minus 1 plus x minus 2 square.
Yes, sir.
So here h1x is equals to minus x minus 3 x minus 1. I think I have written little wrong. This is p1x h, there it was x minus 1 x minus 2 square. First I have to do x minus 1, then I have to do x minus 2 square. So yeah, e1 is equals to t minus 2i square. This is e. And e2 is equals to minus t minus 3 identity, t
Hmm.
minus identity. Yeah, this is the correct one. So e1 is equals to this and e2 is equals to this, and obviously e1 plus e2 will be, uh, as this one is the case, so obviously e1 plus e2 will be identity, there is no doubt. So c1, that is e1 plus
Well,
minus 2e2, this is the diagonal part, and so nilpotent part is n minus d. Yes.
sir, you have, sir, also written E1 as t minus 2i whole square, E2 as t minus I, sir.
No, e2
You
is
should
equals
have.
to, oh no, this is not correct, this is not
Yes,
correct.
sir.
Yeah, this is the correct one. As 1 is equals to this, as 1 equals to this, so this is the e1 and this is the e2. E1 is something where x minus 1 will not be there, okay, and e2 is
But
something where,
we can also change the order, no, sir. There is
no,
nothing, sir,
there is
about
the
order.
coefficient thing. Coefficient is the thing, na? Coefficient is
Uh,
the eigenvalue.
yes,
C1
sir.
E1 plus C2 E2. So if we change E1 E2, C1 C2 should change also, right? I mean, I
Yes,
can't
sir.
write
Yes. So
C1 E2
C,
plus C1.
CIs are eigenvalues, sir, basically.
Yes, CI eigenvalue. So corresponding to CI, we have to fixed EI. Uh, EI are not
Okay, sir.
same.
Got it.
So I'm not calculating it again. So EI is this one, yeah, and E2 is this one. Yeah, actually, this
Yes, sir.
way, I think I have seen somewhere this way finding this, what is called, whenever you have GCD, I mean, whenever GCD of two terms
Yes,
is
sir.
1. No, no, polynomial also
In
this
case,
way is working. There is a way, this
in
same
case
way.
of sir number, sir, in case of number theory, sir, we find this, sir.
Yes, there it is. I have
You
also, but read there
basically
also.
using, sir, Euclidean algorithm is, sir. This is called,
Right.
sir, Euclidean algorithm.
Yeah, there also I have read, but very long, yeah, so I forgot actually.
Yes,
That's the problem. Okay.
yes, sir.
So this way I am not calculating. This will not be that much. This is so you have to calculate that a minus 2i square. This is as e1, and a minus 3i into a minus I. This is as e2 minus of this. So this is as e2, and this is the diagonal operator. And I think I'm not checking here, but this will be correct. I think there is no problem. Okay. So let's do some problems from the last year assignment. This is the problem. Yeah, yeah, this is correct. Okay, so this is problem, another problem. So what it says, let V be the space of continuous real valued functions on the interval minus 1 to 1, and let W and W naught be the subspace of V consisting of even and odd functions. So just want to know, this even function is means a function such that f of a minus x is equals to f of x, that is called even function, and odd function is something such that g of x, g of minus x is equals to minus g of x. Okay, so this is even and odd. This is the what even and odd function definition. So now,
Yes.
so we is taking as all those function from -1 to 1 to interval -1 to 1 real numbers, such that f of minus x is equals to f of x, and w naught is equals to all those function from -1 to 1 to r, such that f of minus x is equals to minus f of x. Okay, so this is what w and w naught. Okay, now what is question is that v, then which of the following statement is not correct? So obviously v is always v can be written as the direct sum of even function and odd function. How it can be written, that I'm just trying to say here, just little bit of
Sir,
uh,
fx can be written as f of x plus f of x minus by 2 plus f of x minus f
that's
of
true,
minus x by 2, sir.
that's true.
Where sir
So
f of x plus f of x minus
yeah,
by 2
same way you have seen
given
maybe for matrix writing as symmetric and skew symmetric. Okay, so
yes, sir,
for
yes, sir.
any function -1, 1 to r, one can write f of x is equals to 1 by 2 f of x plus f of minus x, and plus 1 by minus 1 by 2 f of x minus f of minus x. So one can take the full term as the I mean, I think one can write, if you want to write it as addition, so you have to write the minus first, f of minus x plus f of x. Then clearly, if we consider it as a gx and this is an hx, then g of minus x is equals to 1 by 2 f of minus x plus f of x. So this is again gx. And if one write h of minus x, that is equals to 1 by 2 f of x minus f of minus x. So one have to take common to get it is again an hx, f of minus x minus f of x. So this is equals to minus of h of x. Okay, so this way one can write. So this is always correct, this is correct. So this is not the option, that's what is the my point. This is not, because you have to find the incorrect option. Second is that t is indefinite integral operator defined by this way, then w net and w are invariant. That is also, this is not correct. I mean, as an answer of these questions, this is not correct. Why this is not correct? For
Sir,
option B, yes,
sir, every
yes,
real number is an sir or even function, na sir? Can we say that every
yes,
constant
yes. Every,
thing?
and when you integrate it, it will get x, something of x. So that is odd function. That is
So
what the option. That's
here,
true.
sir, here we take sir if one
Yeah.
as a even function and then integrate will get x, but this is not sir even
This
function.
is one is an even function.
Yes, sir.
Is an odd function. This is an odd function. So
Hmm.
WE and W, read odd and even, are not invariant.
Sir, for odd, sir, we should take, sir, x cube, sir.
Yeah, that same thing. X cube, that will get the x to the power 4, even x that will go to x square. So the same way one. So as a answer of these questions, this is correct, this is false. As an answer of this question. Second is that if E is an operator from V to V defined by EF equals to this way, the null space of E is W naught. I think this is correct. Let's see. E from V to V defined by E of f is equals to f of x plus f of minus x by
This is
2.
basically the
Oh, this is correct option. So that means not
projection operator, sir.
projection on the event space, right? Projection on the space.
Uh,
So for that, null space is W naught, obviously projection,
yes,
right?
yes, sir.
So let's still check it is. So what is the question? Null space. So if from -1 to real value, such that
Null space
e
is, sir, odd,
ef
odd.
equals to 0, that means f of x plus f of minus x is equals to 0. That shows f of minus x is equals to minus of f of x. That implies f in the null space. And conversely, if something is in null space, that will again be there, because in that situation it is that is f of x equals to minus of f of minus x. So if you replace here, so you will get, so that means null space of E, that is subset of W naught, and W naught is subset of null space of E. That is very much clear, because if some function is odd function, that is f of minus x equals to minus of f of x. So if you can replace here f of minus x by minus fx, then it will become 0. So that's why then W naught will be subspace of null space. So that means null space of E is equals to W naught, and best way is that this is projection on W naught, W even. So therefore the null space is W naught. So that means
Yes.
as a statement this is correct. So that means the answer is not wrong for this option, this questions. Second is that is the operator defined by the range
This
space
is
of
correct.
E is WE. That is false, right? Because here it is range space should be W naught. No, sorry, yeah.
So this is correct.
No. Range space of E is
Even
W.
W is you mean even. Yes, sir. Yes, sir.
Yes, even. So this is odd
Sir, I
function,
am
na?
confused with
Yeah.
no.
If I take f is an
Yes, sir. That is correct.
range is, so that means that is correct. That is wrong. So that means answer is
WO.
correct. W uh, odd will be
Yes,
W,
sir.
O
Yes.
will be the range. Okay.
This is the
So
only yes, sir.
yeah,
Statement. It is.
this option. Yeah, let's do this one also. This is maybe easy. So what it says, let V be the space of all polynomials. I am thinking to, from next class, I am thinking to create some problem from my own. This problem or given problem from NPTEL. Okay, let's see. V be the space of all polynomial functions fx over C such that degree of fx less than equals to 4, and D be the differentiation on it, and D is the differential operator. We know the standard order basis of here what it is taken. Uh, V be the space of all polynomials over 4, space of all polynomial of degree less than equals to 4. P with the space of all polynomial degree less than equals to 4. Then then 1 x square x cube x to the power 4 is standard ordered basis of V. Now what it is saying that A be the differential matrix D is the differential operator. Sorry, A be the differential, D be the differential operator. A is the matrix of D with respect to this standard ordered basis. Then what will happen? This is something. This then which of the following statement is or are correct? That is asked. So D on 1 is equals to 0. D of, so this can be written as 0.1 plus 0.x plus 0.x square plus 0.x cube plus 0.x to the power 4, and d of ax is equals to 1, and I'm not writing similarly, so d
Sir,
of
only
x
sir,
square is
one is
equals to
correct, sir. Option A is correct.
a is nilpotent, that's true. D of x cube is equals to 3x, and d of x to the power 4 is equals to 4x cube. So therefore a is equals to, that is d with respect to standard order matrix. This will be 5 by 5 matrix. The first column is 0. Second column is 0. No, not 0. This is 1.
One.
This is
Zero,
1,
zero,
0,
zero.
0, 0, 0. Second is
Zero,
0,
two, zero,
2,
zero.
0.
Zero,
So
zero, three,
0
zero.
0 3 0 0 0 0
Zero, zero,
0
zero,
4
four,
0.
zero.
I think correct, right? This is, so
Yes, sir.
therefore the characteristics polynomial of A is
X
x to the
to
power
the
5
power five.
equals to 0. That implies the minimal polynomial, that implies A is
Nilpotent.
nilpotent via Cayley-Hamilton theorem.
Yes,
Nilpotent
sir.
via Cayley-Hamilton theorem. Because all these things we already have done all these things for a long time ago, so those things need not be mentioned as much. And
Is
where
about
A
minimal
is,
polynomial.
yes, this is
Sir,
correct
what,
option.
sir? What is what can be said about sir? Sorry, sir. Minimal polynomial of this
Right.
matrix.
So that is what the questions then it is. Whenever it is comes to the questions, diagonalizability. So question is the minimal polynomial. What is the minimal polynomial? Clearly, minimal polynomial is clearly x equals to 0 is not minimal polynomial. Okay, so let's me write it some theoretically. Then minimal polynomial of a is x to the power k for some integer k less than, so for some positive integer k less than equals to 5, right? Because minimal polynomial should be lower than something, right? But clearly k is not equals to 1. Why k is not equals to 1? Because if k equals to 1, minimal polynomial will be x. So
G
that
is
means
zero
matrix
matrix.
should be 0 matrix.
Yes,
In
sir.
that situation, a is 0. As when k equals to 1, a should be 0, but that is not the case. That is not the case. So therefore, this is saying that x is not the minimal polynomial. So this says that the operator is not diagonalizable. D is because as 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 a or d, whatever, a is diagonalizable if and only if its minimal polynomial is completely factorized. Not only completely, is the product of distinct linear factor. Product of distinct linear factor. So that means if something is x
This is
square,
not diagonal.
yeah, if the
Yes,
polynomial is x square, that is not the product of distinct linear factors.
yes,
This is product of two same linear factors. So that's why it is, I mean, basically it is saying that a operator is diagonalizable if and only if its minimal polynomial is something like x minus c1 all the way x minus ck, something like this. But here only eigenvalue is 0. So
sir.
x is the option. Yeah. Yeah, and say saying anything?
A nilpotent is realizable only when it is zero matrix, sir. If and only if it is a
Yes,
zero
yes, yes, yes. The
matrix.
same thing. Yeah, nilpotent open matrix is diagonalizable if and only if it is zero matrix. That is the one can say from here. So A is not diagonalizable. This is correct. So here question is that then which of the following statement is correct? Okay. So this is correct. So now the rank of A is 3. Okay. So here you can see that rank of A is 4 because we have 4 non-zero matrix, and this is at least row reduced, maybe not in echelon form, not in row reduced, but if you do row reduction you can know that you can't make this entry this entry 0, only you can do make this entry 1. Okay, you can't make this entry 0, so that means it has 4 non-zero row. Okay, which is not possible to reduce even after doing row reduction process, because you can add row, you can we can do the row operation on row. So if you add two
Yes.
row, still those element will those term can't be making 0. So that's
Sir,
why
this is a row equivalent form, na, sir?
this
In row
is
equivalent form.
row equivalent form. Only the 2 3 4 that should make 1. That's that said, that can be done by multiplying 1 by 2 1 by 3 1 by 4. That's okay. But yeah, that's
Yes, sir.
it
Yes,
is
sir.
it is it is
Yes.
nearly it in Zorides form. So clearly A has row rank 4. So that implies C is not correct, because the option says that rank of A is 3. That is not correct. Third is the Jordan canonical form of A is this. This is not true because, okay, so for that we have to
The
write
rank is
minimal.
not same.
No, rank is 3. That is false. So that says that this is false, right? We don't need to go anywhere because
Yes,
this
sir.
matrix has rank A. two matrices are similar, then they must have rank similar. Okay, if
But how
given
can we proceed from the minimal polynomial?
minimal polynomial is very way that is known that Jordan canonical form. We have to go Jordan canonical form there. Suppose the minimal polynomial is
Yes.
uh, x.
No,
Here
no, sir.
minimal.
How can we find? Sir, I want to find Sir Jordan canonical form of A, sir.
Yeah, that I'm
Then
going
how
to
can? Yes, sir.
discuss for some different problem. But oh, how one can find Jordan canonical form? Yeah, that I'm going to discuss for different problem. But yeah, here I'm just for example, if you know the Jordan canonical form, so then this is these two matrices. I mean, Jordan canonical form is the similar to the main matrix, right? So that means that
Hmm.
then they should have same rank. But here the Jordan canonical form has three rank, so that means the matrix can't have.
So that is correct, sir. Sir, I want to ask if we have, sir, some nilpotent matrix, sir. Then
So how to
what
find
is the
the
quickest way? Yes, sir. Minimal polynomial. Is there any quickest method, sir?
Qt method? I don't know. Only way is that you have to do power and
Yes.
check when it is becoming zero.
Yeah. Yes, sir. Yes.
You can do the
Okay, sir.
calculation as quick as you can. That is
Okay,
what.
sir. Okay.
But there is no other way, I think. Huh. Diagonalizable or not,
That
that is,
that method I know, sir.
yeah,
Okay, sir.
that is what I think. No other, yeah, I mean, minimal polynomial is something you have to do from your own. I mean, that
Yes,
when
sir.
the matrix is satisfying some polynomial.
Okay,
There
sir.
is, if you know Jordan canonical from there, you can say that is okay. If you know Jordan
Yes.
canonical from there, but Jordan canonical form, if you want to know Jordan canonical form, you need the minimal polynomial.
Yes, sir. Yes.
Okay, let's do this. This is after that I will try to go some Jordan canonical form because that is what very important for anyone. Okay, so what it is says, let T be an operator from R4 to R4 such that rank of T is 2. Okay. Suppose that the minimal polynomial T decomposes over R into product of linear polynomials. Product of linear polynomials does not saying that it is distinct or not. Okay. Then which of the following statement is or are correct? T is diagonalizable and nilpotent. T is diagonalizable. If T is diagonalizable, they can't be nilpotent. That is clear. Okay. Uh, okay, let's do this problem. Okay. I think there is some network issue. I think there is network issue. Okay. Let T is the linear operator such that rank of T is equals to 2. So that means null space of T is equals to 2. Right? Nullity of T is 2 because rank plus nullity is 2. That implies x square is the factor of characteristics polynomial. Okay, this should be the factor, I think. Or x is factor, that is what at least for sure. X square is also factor. Okay, for what is the x is a factor, that is for sure. Okay, first question is T is diagonalizable and nilpotent. That is only will happen if and only if T is zero matrix.
Why, sir?
That
This
is
is
what you
due.
just few minutes
Yes, sir.
ago you were saying, na?
Yes, sir. Nilpotent is given. Yes.
Yeah, diagonalizable if and only if that is zero matrix. But
Yes.
so that we can write T is diagonalizable and nilpotent because diagonalizable means the minimal polynomial will be x. Nilpotent means the minimal polynomial xk equals to 0 for some k. But here it is saying that k is 1. So that means this is becoming 0. So, so nilpotent, diagonalizable and nilpotent if and only if t is equals to 0 or matrix representation of t is 0. That implies that t is 0. Representation of t is 0. But rank given that rank of t is equals to 2. So therefore t can't be 0. So that means this option is not correct. T is diagonalizable, then it cannot be nilpotent.
This is
This is correct. Because if T is
yes.
diagonalizable, minimal polynomial is x. So that means it is satisfying A sorry, T is diagonalizable, then minimal, it is not nilpotent, because if it is nilpotent, then we can do same way, that it is 0, but it is not 0. So that's why if T is diagonalizable, it can't be nilpotent. That will come from this argument. If T is diagonalizable as well as nilpotent, it will be 0, but that is not the case. So therefore, if T is diagonalizable, in that situation, nilpotent can't be taken. If T is
Option C is
nilpotent,
correct.
huh?
Option C is correct.
The same way, if T is nilpotent, then T can't be diagonalizable. Because if it is nilpotent, then x to the power k equals to 0. If it is diagonalizable as well as x equals to 0. So that is not the case. T is neither
Yes, sir. B
diagonalizable nor nilpotent.
not correct.
That is not correct, because one can consider 1 0 0 0 0 1 0 0 0 0 0 0. This is diagonalizable. Maybe not nilpotent, but diagonalizable, right? So it is saying
Yes,
that it
sir.
is neither diagonalizable nor nilpotent. That is false. So this is incorrect. Okay, let's go to, then is similar to diagonal matrix. I just want to first do the Jordan canonical form. Yeah, this is something Jordan canonical form problem. I will do this one after that whatever problem, because at least one problem should be from Jordan canonical form.
Sir,
Yes,
sir, what is your area of research, sir?
my area research operator theory.
This is subjected to this, sir, linear algebra.
Yeah, operator means this operator, but obviously that is some little advanced. Just give me for the charge only. Okay, 1 minute
So
only.
that means you have, sir, profound knowledge of linear algebra, sir.
Yes, I believe I have at least.
Yeah, yes, sir.
Yeah, actually, yeah, my linear algebra knowledge is, I believe it is good, but that obviously, just 1 minute to give me 1 minute, because I need to connect charger. Yeah, sorry for the interruption. Yeah, so here it is, question is that V be the vector space of dimension in over F, and T be a linear operator. Okay, so T be a linear operator on V. Let the minimal polynomial of T is this one. Let the geometric multiplicity of F3 is, okay. So I will do something, some theoretical type of things. Obviously, here I will just only talk about the way of finding Jordan canonical form. Okay, I know those type of problems nowadays. It did not came those type of problem nowadays, not directly. At least if it comes, there will be two option which is easy, and other two option which is far away from easy. So
Sir,
will not.
from theory part.
Yeah. Okay. So let T from V to V. Let V be a vector space of finite dimensional vector space. V be a finite dimensional vector space over a field F, and which in general will be either complex or real. So, and let dimension of V is equals to n, and T from V to V be a linear operator, and characteristics polynomial of T is fx. Let fx is equals to given by x minus c1 whole to the power d1 all the way x minus ck whole to the power dk. So therefore, that implies summation of di I equals to 1 to d, I equals to 1 to k, that is n. Okay, and let px is equals to x minus ci whole to the power ri. I think I'm using ri most of the time. Yeah. So okay, I maybe from my side there is an internet issue. So but I think this internet issue is for the full day. It's showing here. So let's ri to x minus ck whole to the power rk. Okay, where ri are integers and they are less than equals to di, and c1 all the way ck are distinct distinct eigen values of T. So now algebraic multiplicity of the eigenvalue Ci is equals to Di. We know that. And the dimension of the null space of T minus Cii is called the geometric multiplicity, or the eigenspace, the dimension of the eigenspace corresponding to the eigenvalue Ca. This is what. Now this is called geometric multiplicity. Now, how to find Jordan canonical form? That way I'm just going to. There is a profound way. I mean, that way first we have this what is called primary decomposition theorem, and from that primary decomposition theorem, I think whatever way it is given in this course, there that the faculty is going through the way to finding generalized eigenvectors, and corresponding to each eigenvalue there must exist some Ri number of generalized eigenvectors, and those Ri number of generalized eigenvector will give those things. Okay, so now, so as clearly note that here I can write, note that T is triangulable. Why triangulable? Because the characteristics polynomial is completely factorized into linear factors. Okay, now there must exist corresponding to
Sir,
each. Yes,
sir, if any operator is triangulable, then it has
every operator is not
vector.
triangulable. Every operator is not triangulable.
No, sir, I am asking, sir. This is our hypothesis. I am asking question, sir. If a if a operator is sir triangulable, then it vector space has vector space has T invariant subspaces of all dimensions, sir. When we say this, sir.
I think that's true. I think that's true. The way this triangulable thing is proved, that is saying that every dimension means obviously from, if it is dimension n,
Yes.
then from
And then
1
yes,
to n,
one, two, three,
1 to
yes,
n. Yeah,
yes, sir.
that's true. That's true. That's very interesting observation. I think you can keep it. Is that if it is triangulable, then it has every degree, every dimension invariant subspace. Take every integer, and that will have that dimension, that dimension subspace is there as an invariant subspace.
Sir, how can you prove this, sir?
Oh, how can I prove? Yeah, that is okay. I can do, but okay, let's do this problem. Okay, then I'll do that one. Okay,
Okay,
that
sir.
is not very long term. That may take 5 minutes.
Okay,
Okay,
sir.
corresponding to each eigenvalue Ci, they are the Jordan canonical form. The Jordan canonical form must contains a block of the form. This is Ri I'm taking. So corresponding to this Ri is something like Ci 1 0 0 all the way. I'm writing as Ri. I have to write. So 0 Ci 1 0 all the way. It will go 0. Second last one will be Ci. This is Ci, this is 1, the last one will be Ci. So this is an R by Ri order block matrix. This is matrix, this is not block matrix, order matrix. So that means what I just want to say, suppose I have the characteristics minimal polynomial is something like C1 to the power 2, then we must have at least one factor of this way, 1 0 0 C1. We have to. If the minimal polynomial contains a factor, this factor is there corresponding to the eigenvalue C1, then we can write 0, C1 1 0 0 C1 1 0 0 C1. This factor, at least one factor will be there, and that in general order is saying that that factor will be in above. I mean, whenever this Ci is starting, if you okay, how this above, that I'm just going to say a little later. But first factor is this, and all other factor, and corresponding to each eigenvalue Ci, the Jordan canonical form must contains a block of the form this. First thing is that, and all other blocks, all other blocks, all other similar type of blocks corresponding to the eigenvalue Ci must have order less than equals to Ri, and total number of blocks corresponding to eigenvalue, this is one fact, this is another fact, eigenvalue Ci is equal to geometric multiplicity of Ci. That means the dimension of the eigenspace corresponding to Ci is the number of block. Okay, and for example, if I take very easy, yes,
Sir, this condition will automatically come from this
right,
Jordan
right,
canonical formula.
right,
This is
right.
not needed, na, sir?
No, this condition automatically come whenever,
Yes.
I mean, this is the, I mean, founding theorems. Those
Right.
theorems is developed in such a way, this, I mean, what is the Jordan canonical form of a matrix? The idea is that if a matrix is diagonal, then that is very simple matrix. One can do very easy mathematics using those diagonal matrix. So if it is diagonalizable, then it is possible to have written as a diagonal matrix by both pre and post multiplication by P and P inverse for some matrix P, invertible matrix P. But if it is not diagonalizable, then what is the best, simplest way to write a matrix? That is the question. To answer that question, the Jordan canonical form comes. Jordan canonical form is something very simplest form of a matrix. And what that simplest form says, that is saying that for a matrix A, we have a very absurd form. I mean, every term is 3, 4, there is no pattern, something like that. Okay. Now, Jordan canonical form says that this matrix is similar to a Jordan canonical type of matrix. Jordan canonical type of matrix, something like C1, 1, 0, C1, something like block C1, C2, C3, something like this matrix. So whenever the entries of a matrix is becoming 0, the number of entries of a matrix is becoming 0, calculations is being easy. Whenever you are trying to make a code of some computer, I mean some code, you want to make code to something doing with matrix. Code means computer code. Okay, some computational you want to do by using some theory, I mean making a code, and you just want to enter the numbers. So if as much as the 0 will be there, the calculation will be easier and will take short time.
Yes,
So
sir.
that is the target to make the Jordan canonical form. Okay. So now I'm just giving a shortest, just trying to give an examples. For example, 3x minus 2 square is equal. This is the characteristics polynomial of matrix sum matrix, and let's write x minus 1 square, x minus 2 is the minimal polynomial. So how the Jordan canonical form will appear? First, look at the minimal. Let's take fixed eigenvalue 1. Look at the minimal polynomial and corresponding to that factor, x minus 1 whole square. So that means corresponding to that factor, okay, let's write it 3. I just don't want to make 3. So then there must exist one block of this way. If the minimal polynomial is, for example, suppose 3, then the block will be something like this. First block will be this way. But okay, so just to give an example, I'm writing 3, but here I'm writing 2. So this is the first block, it will be there. So let's write this way. And all other block will be less than equals to that order. I mean, all other block order will be less than equals to that order. Less than equals to that can be equal. Less
There
than
is a
equals.
one cross one
There
block.
is only one option here, and that is 3, right?
Yes.
But I'm just, for example, if I am writing 4, for example, if it is 4, therefore, then there will be two possibilities then. 3, 1, 0, 3, and Either it
Three.
can be 3 3 this way, or
Uh,
0 3 1 0 3 that way. Okay, this is
yes,
the
sir.
way. And the general order is that first to write the bigger block and the smaller block.
Yes,
So
yes.
I'll write 3 here, so I'll not write this one. Okay, so this is not there. Okay, so this is the thing. So similarly for the other one will also similarly. So here we don't have the geometric multiplicity. For example, of geometric multiplicity of 3. For example, here we have 4, and the geometric multiplicity for this case will be 2. Sorry, 3. If it is written like this way, and geometric multiplicity will be 2 if it is written like this way, right? If it is geometric multiplicity is given, then it is precise. If geometric multiplicity is not given, then it is not precise. We can have both two. I mean, whenever the power is 4, that situation I'm just talking about. So, but yeah, here I am talking about. Here I will do the. I'll write that one only. Okay. So give example. I just want to change. I'll change those way. So similarly for all other will be there. So this is 3, and automatically here we have 2. Only one block here is there, and automatically other block is less than 1. So you can understand why the diagonalizable operator, whenever the minimal polynomial is completely factorized, why the diagonalizable operator in the Jordan canonical form is diagonal. Because minimal polynomial is whenever it is completely factorized, then the highest degree block will be of degree 1, order 1. So that's mean all other will be 1, right?
Yes, sir.
Yeah, it's clear, I hope. Okay, so let's go back to the problem. Okay, I'll write. uh, okay, just 1 minute. I'm removing from here. Just a minute. Yeah, just a minute. Yeah. Hmm. Sorry, we'll take time later. Just a minute. Okay, so let's go to the problem. That problem. I'll do that problem. After that, that triangulizable thing. I think this was the problem. Yeah, this is the problem. So here it is said that V be the vector space of dimension n, P be the linear operator, and the minimal polynomial is given. The here Px is equals to x square minus 9 and x minus 5 square x plus 7 cube. Let the geometric multiplicity of 3. So geometric multiplicity of 3 is equals to 2, and geometric multiplicity of minus 7 is equals to 2. Then J will be possible Jordan canonical form. That is what asked. So minimal polynomial is this. So what is the so therefore one can write this is as x minus 3 x plus 3. Okay. So x minus 3, x plus 3, and this is x minus 5 square and x plus 7 cube. This is what we have already, right? So now so therefore geometric multiplicity is saying of 3 is 2. That says the algebraic multiplicity must be greater than or equals to 2. So that means question is
Sir,
yes.
what is the question, sir?
What is the?
Sir, can you show the question again?
Okay,
Questions.
that's yeah. This is the
Can you
question.
show the question again? Yes.
Yeah, this is the question. It is visible, right?
Yes, sir.
Hmm.
Sir, I think there is something wrong, sir. I think.
No question. There is no wrong, I think.
So let the geometric multiplicity of 3
Huh.
is 2.
3 is 2. Okay, and minus 7 is
Okay.
2. Geometric multiplicity of minus 7 is 2. What is the? I mean, geometric multiplicity is 2.
Sir,
That are
cannot
that
be, sir, cannot be 2, sir. 3.
no.
Geometric multiplicity of 3 cannot be 2, sir. Because, sir, there is, sir, only one term of x plus x minus
That
3
is
is.
minimal polynomial, not characteristic polynomial. For
Yes, sir. Yes, sir.
example,
Yes,
got it,
sir.
na?
Yes.
Huh,
Okay, sir. Got it.
huh. So that is the reason. So geometric multiplicity can be whatever it is written. Okay. So therefore, and the geometric. So therefore, okay. Let's do for 3. So that is as the minimal polynomial has one factor of minus 3, one factor of 3. So the Jordan canonical form is. So first 3 is the factor because minimal polynomial contains only one factor, and the geometric multiplicity of 3 is 2. That means 3 will be repeat twice. I don't know what times minus 3 will repeat. I'm keeping it is, I mean, that is minus 3 correspond. I don't know minus 3 what time it will repeat, that I'm keeping now. But now if we consider the minus 7, the minimum block will be of 3 by 3 order. So let's write the minimum block of order 3 by 3. But what it is saying, it will repeat twice.
There is minus 7, sir.
Yeah. So this will be minus 7, 1, 0, 0, minus 7, 1, 0, 0, minus 7. So now
Sir, we
what?
can also take only minus 7, na, sir. 1 cross 1 block, sir, corresponding to minus 7.
That's true. Exactly. Yeah, sorry, very mistake. Yeah, that is also possible. That is also possible. So now what we have left?
Actually, sir, this is not
One,
possible, sir, at all, sir.
huh?
This is not possible, sir, at all, sir.
What is not possible? Yeah, that is not
Sir,
possible. What I have written, what I had written, that is not possible. That's true.
yes.
That is what I'm just coming. Why that is not possible? So then it will automatically give the okay. So
There is
these are
1
the
cross 1.
minimum factor we
Yes,
should
sir.
have, right?
Sir, there is also 1 cross 1 block, na, sir.
Yeah. So that is what we will count. Now 1, 2, 3, 5, 2, 7, 1, 8. But matrix is about order. So the dimension is n 9. So therefore there must exist another
Yes,
factor
yes,
of corresponding to minus 7 of that is of
sir. Sir,
this
it
is.
is given, sir, geometric multiplicity of minus 7 is 2, sir. So
That's
you have
true,
considered
but
that part.
if it is written here that it is 10 instead of 9, so that is what I
Yes.
just want to count. That is what I'm just want to point out. That it is 9, that's why the geometric multiplicity says that it will have two factor, right? Suppose here the dimension of the vector space V is 10 given, for example. In that case, there is three possibilities will come. One possibility is say that it will have minus 7 minus it will have minus 7 3, that way is possible. Minus 7 1 0 minus 7 is possible. Okay, these two is possible, and also possible minus 7 minus 5 is possible, right? All this possibility will be entered if the total dimension of the vector space V is 10. Got it?
Hmm.
So that's why the only one factor minus 7 will be there. There will not be a factor minus 3. There is not possible to have this 2 by 2 factor. There is not possible to have minus 7 minus 5. 3 will not be here because 3 is saying that geometric multiplicity of 3 is 2. So that is 3 is exhausted. Okay. So now what is not given? That 5 is not given and minus 3 is not given. So that means that can repeat, but it is given geometric it is giving that the dimension of V is 9. So that will make sure that there is only other factor, and that is of only 1 degree. So this is the Jordan canonical form. So therefore this is the, I think minus, yeah, this is the correct option. All other option will be automatically false, because you can look at there -7 that is not possible. This is not possible at all. -7 this is also not possible, and the last one is also not possible because there is 5 is not put correctly. Okay, now let's get back to your questions. That if we have a triangulable operator, so every corresponding to every degree, every n, I mean I less than equals to 1, we can get an invariant subspace. That is what
Yes.
your question, right? Okay, that can be looked at very easily. Why it is very easily? Okay, first of all I will give, so let's write the statement. Let V be a vector space over a finite dimensional vector space. V be a finite dimensional vector space over a field F, and let's take dimension of V is equals to n. T from V to V be a linear operator. Then if T is diagonalizable, T is triangulable, then for each k, for each positive integer k, for each positive integer k less than equals to n, there exists an invariant subspace, wk such that, oh, there is an invariant subspace wk. That is what your questions, right? There is an invariant subspace wk. Invariant is invariant with respect to t. That is what your questions are.
Yes, sir.
So I'm just going first. I'm just showing. I mean, I'm not trying to say why this is true. Then I'll say. Then I'll prove. Okay. If it is triangulable, so that means there exists an order basis with respect to which the matrix is given by this way. 2 2 all the way 2n, all the way it will be an, right? So there must exist an order basis with respect to which matrix is given by this way. Now let's that order basis is x1 x2 xn. This is the order basis. Then let's take x1, I mean if you want to take wk, then take x1 all the way xk. Then this is invariant. Why this is invariant? This is the matrix representation of T with respect to this order basis x1 x2 xn, right? That is what I mean. Triangulable means that there exists an order basis with respect to which matrix representation is given by this way, upper triangular matrix, like, okay, either upper or lower. But for example, I'm just without loss of generality, I'm taking upper triangular matrix.
Sir, can we define triangulable operator as like ki, just ki, uh, there exists an invertible matrix P such that P inverse AP is sir, similar P inverse AP is equal to T, where
Yeah,
T is a
that is
triangle.
that's true.
In
That
this
is
way, we can define sir,
that way.
triangulable.
Obviously, that way you can do. There is no problem. I mean, whenever suppose the matrix representation of T with respect, this is suppose A matrix A. So A is triangulable matrix. So suppose T has a order, I mean, let's take any order basis of the vector space V, and the matrix representation of T is B. Now, if BT is triangulable, that means there exists an invertible matrix P such that PBP inverse is equals to a triangular matrix A. That is possible.
Yes.
So how this
Okay.
is possible? Okay, how this is possible? Okay, let's first of all, I just want to point out one thing. If T is a linear operator, okay, if it is triangulable, that, okay, you need some definition of triangulable, right? What do you want
Yes.
to take definition? Okay, I just want to say some equivalent things, that x minus 1 to the power, I mean, the minimal polynomial or characteristics polynomial is completely factorized. That means something product of x to the power ci to the power some di I equals to 1 to k. All ci are the distinct eigenvalue. This is
Yes.
one way to say that the matrix is diagonalizable. Other way is say that there exists an order basis with respect to his matrix will be looks like this way at upper triangular matrices
Mm.
for without loss of generality.
Yes.
And other characterization is that there exists an invertible matrix P
Mm.
such that P inverse that BP is an upper triangular matrix. Okay,
Yes.
these three definition. Okay, so these three I'm just writing. I'm not right. I'm just trying to formally say. Okay, I'm not writing. If I want to formally
Yes.
say, I have to write the statement properly. But I'm not
Yes.
writing. So these three are equivalent. But these
Mm.
three equivalent means you have to take something as a definition. You have to starting with a definition. You can take anyone as a definition. There is no problem. But if you take there is an order basis with respect to, I mean, these two are for linear operator. For
Mm.
linear operator. This is for matrix.
Mm.
This is
Yes.
also for linear operator, but that linear operator is correspond to the standard
Standard
order
that.
basis. Standard order basis. That's true. So that is what. So whatever you can start. Suppose I am taking T is a linear operator from the let's take R3. Let's take it is complex field to complex field. There, Cn to Cn. Okay, this is linear operator. Cn must have some standard order basis. So if I want to represent T with respect to standard order basis, we should have some matrix representation. But P is triangulable if there exists an order basis of Cn with respect to which matrix is triangulable. That does not guarantee that with standard order basis the matrix will be triangulable. Standard order basis with respect to standard order basis matrix may not be triangulable. I mean may not be triangular matrix. But I can get an order basis with respect to which the matrix of T, order basis of Cn with respect to which matrix of T will be
Triangulable. Triangular.
triangular, right? So, for example, the matrix of T with respect to standard order basis is B, right? And suppose I am getting an ordered basis x1, x2, xn with respect to which the matrix is triangularizable matrix operator A. It is triangular matrix. Okay. Now, this standard order basis something if I write e1, e2, en, that means 1, I position 1, all other integers 0. Then there must exist a linear operator which transforms these two operators, these two order basis, which maps ei to xi. Okay.
Change
That
of basis matrix.
change of basis matrix, that is P. There is nothing fancy, that is P. So if you start with the thing is that there exists an order basis with respect to which matrix is the matrix is triangular
Triangular.
matrix, so that means you have this way matrix. So now
Mm.
if you want to write it in standard order basis, so let's give the change of basis matrix. We'll get the matrix corresponding to standard order matrix and how to make it triangular. You
Mm.
know. Okay, so this is it. But this is also another characterization. The characteristic polynomial is the product of xi minus product of I equals to 1 to k xi minus ci to the power di. So this is what it is taking as the standard definition. Why it is taking as the standard definition? Because this is something in polynomial. Linear algebra maybe comes from the matrix things, but when you want to do some mathematics, you have to go to some analysis, and analysis lies on this polynomials and all these things, functions, all these things. Okay, so I'm removing these things. Okay, I think this is clear how to go if it is triangular if, I mean if it is there exists an order basis with respect to which so with respect to standard order basis the matrix is given, and if I want to make it triangulable we have to go that basis which is triangular, which making it triangular. Okay. Okay, so now let's go to your problem. Okay, I just want to write first how why I just want to write first why this is possible. Suppose there exists a basis with respect to his matrix is given by this way, right? So now if you consider WK, then this is invariant corresponding to K. You can take the span linear. This is the WK is actually not the this x1 x2 xk. WK is equals to linear span that is given by this symbol.
Bracket.
Yeah. So then this is invariant under K. Why this is invariant under T? Why this is invariant under T? So any element alpha belongs to wk must be looking like this way: ci xi I equals to 1 to k, right?
Yes,
So
sir.
that means matrix with respect to the standard, and this is what standard order basis, I mean full order basis, you can be right? So matrix with, I mean this column vector corresponding to this basis is giving by something like c1 all the way ck and all other integers 0, right? So now here the linear operator T on this matrix form is given by A with respect to this matrix form. That means the matrix is given by A1, A2, AN, 0, A2 to A2N, all the way ANN. This one, with if we multiply with this matrix A1 to C1 to CK and all other entry 0, then you will get first entry is 0, I mean after the kth position all other entry will be 0. Why? I mean the matrix what I will get, this column vector, that column vector after kth position all other entry will be 0. Because why this is, because I'll just write that it is little bigger, then this will be clear. Let me write it a little bigger, then this will be very much clear. A11 all the way A1n, and suppose we have 0 AKK, k plus 1 all the way a1 a kn, right? 1n. So a kn, this is the matrix, and something next one will be 0 to a k plus 1 all the way a k plus 1 n, and all the way a nn. This is the matrix, right? And I am multiplying with c1 ck 0 0 0. Now if we just go to k plus 1 position, recall that first k term is 0. After that, n minus k term is possibly non-zero. But here first k term is 0, non-zero. And next n minus k term is 0. That means after kth plus 1 term will be 0. Right? Suppose this is kth position is completing. Then kth plus 1 position will be 0. Clear?
Yes, sir.
Now it is clear now that why it is happening, because suppose up to this position we have 0 entry, so that means if we multiply with ck, that will be 0. After that we may have here a non-zero entry, a k plus 1 2 a, this may have non-zero term, but
They will
here we have
become
0
zero.
term, right? So that's why it is becoming 0.
Sir,
Okay.
alpha is sir any sir any vector na sir from W. Alpha is any vector from W, sir.
Yeah, and any vector from wk, right, you are saying?
Yes, sir. Yes, sir.
Any vector in wk, that element can be written this way, because alpha in wk, that means alpha can be written as a linear combination of x1 x2 xk, right? But
Sir,
yes.
so we have to show that T of alpha is in WK, but you are
Right.
considering coordinate vectors of alpha, sir.
The same
Why?
thing, na?
Because,
Okay, we
no,
have, when we are dealing with matrix, I'm just writing here na. Suppose I want to define the vector space V2V, and we are considering a fixed order basis x1 x2 xk xn, right?
yes,
Then
sir.
with respect to order basis, if the matrix representation with respect to this order basis is A, then T, and the column, and then any element of the vector V, suppose beta, suppose we are writing a V is a vector in small v is a vector in capital V. Okay, I'm writing this is something different. Small v is in capital V. Then V can be written as the linear combination of some ci xi I equals to 1 to n, right?
Yes, sir.
Then writing what is the TV, if I want to find what is TV, this is same with matrix of TV and V with respect to matrix of B. And that is what is the coordinate vector. I will get some coordinate vector, right? This is some column matrix I may get. The vector TV will be summation of those coefficients. Suppose this is beta 1 all the way beta n, then beta I xi. This is TV. It is clear what I just want to say from this left hand side portion. Suppose T is a linear operator from a vector space V to V. X1 to Xn is an order basis for V. And the matrix representation of T with respect to order basis B is A. Any element V belongs to capital V can be written as summation of Ci xi, that can be represented as a column vector Cn with respect to the order basis beta.
Yes, sir.
Now, what is the TV? If I want to find it, what is the TV? First, I have to find what is A and this matrix X. If I write this column vector X, then I have to find AX. That must be a column vector. Suppose B1, B2, Bn. Then TV is summation of Bi, Xi, beta I, Xi. This is very
Sir,
standard.
this is the case where in if we write t in the if we write a in terms of sorry standard basis,
No,
then we
no,
can write tx is equal to ax.
right, right. In standard basis, I mean, if I take beta is standard basis, then Tx equals to Ax.
Ah, yes, sir. But here, sir,
No, no,
this
no. Okay, okay. I understand what is your issue. Suppose we are taking an arbitrary vector space V. There may not have standard order basis. We can fix an order basis and say that that is standard, but standard order basis is nothing that it is universal. You have to take it. Standard order basis is some convention. Okay, that
yes,
100 0 1 0 that order is taking as the standard order basis. Suppose V is not like Cn or Cp. Suppose okay, let's take this is Cn. Matrix is Cn, right? The standard order basis is we know what is that ith entry is non-zero, 1 and all other entries 0. Then matrix representation, suppose now any vector x is in Cn must have can be written as summation of xi, ei. That is mean this is column vector x1, x2, xn. But also we know that x is in Cn means something x1, x2, xn. That is why it is called standard.
hmm.
So now the matrix representation of T with respect to the standard order basis is suppose A, then T of the vector X is equals to A with respect to x1, x2, xn, whatever we will get. Suppose we are getting y1, y2, yn, then Tx actually this is not the Tx. Tx is summation of yi, ei. Now replace E1, E2, En by the standard order basis what I have taken as x1, x2, xn. Okay. Then this is also true. There is no problem with this. I am taking, so I mean matrix representation of T with respect to standard order basis is A in that situation. Suppose we are taking V from V Cn and to Cn, and I have taken a ordered basis x1, x2, xn is an any ordered basis. This is ordered basis I need only. And let's take the matrix representation of TB is A. Here, if we are not taking this is standard order basis, then the matrix representation is not A. Then sorry, matrix representation is A, but matrix representation this matrix is not correspond to the standard order basis. Then suppose we are not taking this basis as just for example R3 for R3 the standard order basis is 1 0 0, right? 0 1 0 0 0 1. This is standard order basis, but I can take this set also as a basis. This is an ordered basis. I am taking this is x1, this is x2, this is x3. With respect to this ordered basis, there must exist a matrix A, right? Now, if I want to take an vector x is in V, then x is equals to suppose alpha V is in V. Suppose V is equals to summation of Ci xi. This xi, okay? I equals to 1 to 3. In that situation, V can be written C1, C2, C3 with respect to the this order basis as a column vector. Then if I want to find what is TV here, what we have to do, I have to multiply A with this C1, C2, C3 is equals to whatever the matrix I will get, suppose C1 dash, C2 dash, C3 dash, then TV will be summation of Ci dash xi, this xi.
Okay.
I hope it is clear, but I think whatever you are thinking is that the matrix, I mean, in standard order basis, we are all thing are taking basis is that one, and in another order basis, we are taking all thing are in that basis. There is no harm with this.
Yes.
Okay, I think this is very interesting. I mean, if you have any doubt, please be clear it at least by yourselves or in anywhere else, because this is not. I think you should be clear this doubt, because this is I mean what it should not be problem. I
This is
think.
very important, sir.
Yeah, this is very important because this is some. I think I mean whatever you are doing in standard ordered basis, you will have to do in the other order basis, but you have to make sure that what is the importance with standard order basis. is that suppose we have a vector x is in R3 or C3, then that is equals to x1, x2, x3. So with respect to standard order basis, the column matrix is same. Column matrix is x1, x2, x3. But if we change the basis, then column matrix will not be, with respect to that order basis, the changed order basis, column matrix will not be same. That is needed the basis change matrix there. Okay. So that way, I mean, whatever you can do with standard order basis, you can do with any order basis, but be careful. Whenever you want to multiply a vector x1, x2, suppose we are giving a vector x1, x2, xn, you can't directly multiply with operator a. You have to represent x with respect to this order basis, x1, x2, xn. Understood?
Yes, sir. Then
And
find
what
coordinate vectors, then multiply,
exactly,
then
exactly,
coordinate
that's it.
vectors, then fill. Okay,
Right.
sir.
Suppose you have a given vector x in R3 and the order basis is changed, not standard order basis. You have to write that vector in terms of the new vector, in terms of the new order basis, and whatever coordinate matrix will come, that you have to multiply. That is what.
Hmm.
But when it is standard, you have to standard. Okay, so this way you can say that the okay, this is okay, if that is clear, so then this is clear now that why the elements after a kth position will be 0 in this triangular thing.
Yes, sir. Yes, sir. This is
Okay,
clear, sir.
clear. So add it is clear. So that means this is again in WK, right?
Yes, sir. After multiplying with, sir,
Right, right. Because this
okay.
is already in WK, right? So and one I'll give a short theoretical. Actually, this is not theoretical. This is something I just want to say why it is by looking at the matrix. Suppose the matrix is given. Suppose the minimal polynomial is given by this way. I'll take 1 minute, 2 minutes more. ck whole to the power rk. Suppose this is the characteristics polynomial. Okay, I am taking characteristics polynomial as dy. Suppose dk. This is the characteristics polynomial. Then clearly c1 is an eigenvalue. That must have at least one eigenvalue must have, because
Yes,
if we have a matrix
by
and it is
definition, sir.
completely factorized, this is what
Hmm.
we are taking. The completely characteristic polynomial is completely factorized. So if it is completely factorized, then there must exist at least one eigenvalue. If it is not completely factorized, the eigenvalue may not exist. For example, if the characteristic polynomial is this over the field R, then this is not factorized. So
Yes,
there
sir.
does not have any eigenvalue. Okay, so C1 is eigenvalue, so there must exist an eigenvector V1, right? Okay, so now let's take V1 is an operator. Okay, just 1 minute. Okay, okay, okay. There is an interesting lemma. I think that is that I believe I not believe I have seen that is done. The lemma says I'll write this lemma. Lemma says suppose the minimal polynomial is x minus c1 to the power r1 all the way x minus ck whole to the power rk, and let w be a proper subspace of V, okay, which is invariant under T, then there exists a vector alpha in V such that alpha does not belongs to W and T minus Ci alpha is belongs to W for some eigen value C. What it is saying, let's T is a linear operator from a vector space to V to V, and this is the minimal polynomial. Characteristic polynomial is that way, then minimal polynomial will be only this way. There is known. Now W is a proper subspace of V which is invariant under T. If we have this factor, then there exists a vector alpha in V which is not in W, but after applying T minus C alpha, that is in W. This will be used. Why this will be used? Now, this lemma, how to using this lemma? Suppose the characteristic polynomial is this way, then minimal polynomial must be something like this way. Okay, this is the minimal polynomial. Okay, now C1 is eigenvalue and I know that V1 is an eigenvector, right?
Sir,
V1 is,
sir,
yes?
sir, this lemma, sir,
Uh-huh.
in this lemma, sir, existence of alpha is assumed and
No.
existence of
That is the result. Then there exists. This is the result. This is the lemma
and
result.
for some eigenvalue C.
Yeah, for some eigenvalue, that eigenvalue depends. Okay.
Sir, both the existence of alpha and C, sir, is claimed here, sir.
No. Yeah, that is. I mean, first taking is that let's take W is a proper subspace of V, which is invariant under T. That is assumption.
Hmm.
Okay.
Yes, sir.
If W is proper subspace, then it is saying that there must exist alpha belongs to V such that alpha is in V, but alpha is not in W. But we will find some and alpha such that which is not in W, but T minus Ci alpha is in W for some eigenvalue C. That eigenvalue depends on the alpha.
Okay, sir.
Got it? So these two factors very existential. I mean, these two are giving existential as a. So now, suppose V1 is the first eigenvalue corresponding to the eigenvector corresponding to the eigenvalue V. Let's take span of V1. This is W1. This is invariant because V1 is the eigenvalue, right?
Yeah.
Whatever. This is T of V1 equals to C V1. That means V1 space is invariant. Now, as is V1 is invariant, so there must exist a vector alpha in V, which is alpha is not in W, such that T minus Ci alpha, for some I am taking for some I, alpha is in W. Now, as T minus Ci alpha is in W, so that must be equals to Ci Vi, right? So that means T of alpha is equals to Ci alpha. That is different. Okay, this is, let's take J. That will be distinct from J also. Okay, does not depend. I'm just taking J can be equals to I. That is not a problem. Cj alpha Ci Vi. Okay. So now let's construct the order basis. How order basis? Yeah?
C1 V1, sir. Sir, C1 V1 should be there, sir, na?
C1 V1. That's exactly C1
Because
V1.
W1 is
Like that. C1 V1. But this J can be any J. 1 can also happen, right? That means J can take a
yes.
value 1. So now V1, I'm just trying to construct an order basis. V1 is there. Let's add alpha. And for the sake of simplicity, sake of completeness, I'm writing alpha 2. This was is alpha 2 vector. Okay? To make it clear. So now let's take W2 is equals to span of alpha 2 V1. There must exist similarly some vector alpha 3 such that T of alpha 3 is equals to some Ck Cj dashed alpha 3 plus some vector C j dashed alpha 2 plus some vector C1 dashed V1, right? One can write like this way because similar process. I have taken this is the invariant space. This is invariant now, right?
Yes, sir.
So now there must exist a vector alpha 3 which is in V3 the V but not in W2 such
Sir,
that
how, sir, alpha 2 V1 is, sir, W2 is T invariant, sir.
W2 is invariant. Okay, why W2 is invariant? Let's take any element from W2. V1, P V1 is equals to C1 V1, that is again in W2. P alpha 2, that is equals to Cj alpha 2 plus C1 V1, that is in W2. As the basis is in there, so everything will be there, right?
Okay, sir. Oh, yes, sir. Yes.
So W2 is invariant subspace. Okay.
Yes, sir.
As W2 is invariant, so T of alpha 3. So similarly, I am writing there exists an alpha 3 which is not in
Sir,
W2.
T
Yes.
minus, sir. T minus something, na, sir.
Yeah, so that is what I have written directly. So T minus some vector C I am writing J dashed alpha 3 is equals to this, na? This should be some scalar multiple of alpha 2 and V1,
Yes, sir.
right?
Yes.
So that is I have written, but some order is, maybe some constant are
Okay.
repeating, but that constant may not be repeat. Okay, obviously it will not repeat. Some Cj dash alpha 3 plus Cj dash alpha 2 plus C1 dash V1, something like this, right?
CJ double dash, sir. You can write, sir. CJ double
That
dash
okay. That
to make things different, sir.
yeah, okay. So whatever this is double dash. Okay, so this is the thing. So I have got alpha 3.
Okay,
Now in this way we will obviously end up by getting an n vector because we can't get all the vector always because V is a finite dimensional vector space, right?
yes, sir. Yes, sir.
So therefore we will end up with a vector alpha n. Note that T of V1 is equals to C1 V1. T of V2 is alpha 2 some scalar multiplication plus alpha 2 to V1 like this way. T of V3 is alpha 2 and T of alpha 3 that is linear multiplication of alpha 3, alpha 2 and V1. Right? Right? So now
Yes, sir.
look at the matrix representation. Matrix
You are
representation is C1.
describing sir, generalized eigenvectors, sir. Chains.
Huh?
Chain of generalized eigenvectors.
No, this is not same thing. Yeah, chain of generalized eigenvector that depends that is something that I mean in particular case it will be not always. Whenever all eigenvalue are same, Ci and the characteristic minimal polynomial is raised by some other power is there, so then in that situation,
Okay.
I mean what is called chain of generalized eigenvalue vector that is corresponding to a fixed eigenvalue.
Yes,
But
sir.
here
Yes,
we
sir.
may have different eigenvalue, right?
Yes, sir.
So matrix representation is something like A21, A22, 0, 0. You can look at why the matrix is triangulable, right?
Hmm.
So this is what? This is the constructive proof. Clear it is?
Yes, sir.
Okay, I will obviously not go beyond this. Today's so if it is not clear, you can if there is any doubt, you can ask in any other place or next tutor we
No, no,
can
sir.
ask.
This is clear, sir. So, sir, you have solved my problem in two ways, sir. Actually.
Yes. One is a matrix way, but matrix way is when it is matrix is given. But I mean, for example, if you are asked, say that you are giving, I mean, when you are asking that it has invariant subspace, that means that is corresponding to linear operator, right?
Hmm.
Whenever it is linear operator, as a special case, one can deal with matrix. But whenever it is linear operator, then whatever the available materials, characteristic polynomial, minimal polynomial, all these things. I mean, linear operator and matrix are nearly same thing, but they are not same. Whenever you are saying that invariant subspace, then you are dealing with linear operator. But whenever you have matrix, but for a matrix, directly you can say that you can't say that there is an invariant subspace. That matrix, when you are saying it has invariant subspace, that means you are considering that matrix as a linear operator with respect to standard order basis or some order basis,
Sir,
right?
in finite dimensional cases, both things are same, na sir?
Yeah, both things are same, exactly same. Finite
Uh,
dimensional space is same,
sir,
but
and we do not, sir, tell about, sir, the characteristic polynomial in finite dimensional spaces, sir.
no, there is no characteristic. No, that can have characteristic polynomial can have. Suppose you are taking an identity matrix. Characteristic polynomial, no, there is no characteristic polynomial. Minimal polynomial is maybe possible, but
Sir,
those things are actually meaningless there.
in case of, sir, infinite dimensional vector spaces, how can we define a triangulable matrix? There is no concept
No,
of
no,
matrix.
there is concept. One can define. You have to generalize this. Nothing else. That is what it is. For it, let's take V an infinite dimensional vector space. For example, you can take space of all polynomials, right?
Okay, sir.
Space of all polynomials. Okay, that means it has the standard order basis 1, x square, all this way. It will go, right?
Yes,
This is
yes,
standard order basis. Let's take
yes.
differential operator. This is a diagonal triangular matrix. But what is the definition of triangular matrix? That is says that T of xk will be summation of ci, or I can write cki xi I equals to 1 to k. Got it? T is an operator. I can write T, or I can give action on some element, x to the power k, right? X to the power k is is an element of the order basis. Now x to T of x to the power k is x, not x, sorry, x to the power I. X to the power I, but sum is taken over up to k. In that situation, automatically element will appear up to k. For example, you can look at the matrix representation where k is 1, first term will be C1, 1. All other integers 0. There is no matrix, but this operator can be said triangulable because it is, if we consider it an infinite order matrix, that matter matrix, the upper element, I mean upper diagonal element will be non-zero, but lower diagonal element will be zero. So triangular matrix, right?
Okay, sir.
So so you can't say there is a triangulable operator you can say, but matrix can't say, because infinite matrix is something one can intuition, one can have intuition but can't say directly. It is not possible to write an infinite dimensional matrix in a page, but it is possible to define a linear operator on a infinite dimensional vector space.
So, sir, what is the sir definition, sir, in case of infinite
That
dimension?
is this is the definition you can say. Linear operator T is triangulable if T of x to the power k equals to I equals to 1 to k c k I x to the power I equals to 1 to k. It should not go beyond k.
Yes, sir.
If we have finite dimensional, you will have the same thing with the diagonalizable. But here, this for all k. So actually, no one is actually interested in triangulable, but with this matrix, this is something. Idea is that, I mean, this is the idea. I am not saying this is the exact definition, but this is the what the gist I just want to say.
Yes, sir. Okay, sir.
Okay,
Thank you, sir.
so yeah, I'm stopping here for today's. Okay,
Yes, sir. Yes,
yeah,
sir. So,
thank
thank
you.